Welcome back. In this lecture, we're going to look at chapter 29, a closer look at tests of significance. And this chapter gives us some of the nuances of the applications of applying inferential statistics and tests of significance in the research context. And there's some important topics in this chapter that I want to draw your attention to. Especially because generally people find tests of significance kind of complicated and mysterious, and it's easy to ignore the limitations of these techniques, to see the tests as black or white, but and reject or retain, but what we actually have is more nuanced. It's important to think about what we can do with tests of significance and what they can't do. So first off, we'll think about, is the result significant? The idea here is to help you remember that the significance levels that we've established, these 5% and 1%, the levels for understanding how small P needs to be before you reject the null hypothesis, these are arbitrary values, more or less. I mean, it's the standard to use the 5% and 10%, but they are just arbitrary, and they don't tell us with certainty. They just give us some a likelihood of chance variation or not. And so but they are significant, and so the point is that if you're, for example, if we look at this small t table, and we'll just start at the 1 degree of freedom level, you can see that the value for 5%, the cutoff here, is 6.31. But if we observed a value, t for 1 degree of freedom, if we observe a t of, let's say, 6.29, is that an extremely different result than if we observed one of 6.33? No, it doesn't really indicate a dramatic difference between the groups, because this line was just an arbitrary significance level. And the reason that these tables have come about, these significance tables, is that they're quite outdated at this point in time. So Fisher was one of the first to come up with these tables, and it was his idea to lay them out this way with specific percentages set up, and because there's a limited amount of room on a page. And once the number of levels, probability levels, was limited, 5% and 1% stood out as nice round numbers, and they soon acquired this kind of magical life of their own. And this magical life imbues with some special power, which is not necessarily valid, but it is reflected in our publication bias, because when articles are being evaluated for publication, there's often a lot more weight given to an experiment that with a result like this one, 6.33, over that very same experiment that maybe found a result of 6.29, even though this difference is not, it doesn't represent any kind of important difference between these in terms of the overall chance. for this result to be due to chance variation or not due to chance variation. And you see this publication bias all over. So this is a pretty antiquated approach. Nowadays, investigators should just summarize the data, say what test was used, and report the exact p-value instead of just comparing p to 5% or 1%. And it's easy to report the exact p-values nowadays because when you compute these test statistics in SPSS, Excel, or another statistical program, you generally get an exact p-value rather than having to use a significance table. It'll tell you the exact probability. And you should just compute that because a probability of, say, 5.05% is still, could be meaningful. And as you'll see, this has other implications when we think about the context of sample size and how that affects our likelihood of finding significant results too. So this is really important to remember that this is just, these are just arbitrary. Another issue is this idea of data snooping. And to help unpack this, remember that the point of testing is just to help us distinguish between real difference and chance variation. And there's a couple of issues here. So one is that when you, data snooping itself is this process whereby investigators take data and look at it multiple times in different ways to try to snoop and get a peek at it and then adjust their tests to get optimized p-values. And it really, when you look at the data multiple times, it has compromises the significance levels, which is kind of a difficult topic to understand, but it's important to keep in mind, at least when you are looking at applying what you've learned in this class to the statistics you see out in the real world. So out in the real world nowadays, we see that we generate statistics at an extraordinarily rapid pace. Just by carrying your phone around, you generate data, generate an immense amount of data each day. And practically everything we do is tracked and quantified in some way nowadays. And it's kind of common practice to look at the data to do more and more of this data snooping. And so when you see results, it's important to keep in mind that the experimental design. So data snooping is more of a problem when there's data already collected and we're just and it's sometimes called data mining, and they're just looking for significant things, but it compromises the p-values. Now, another topic in this section that's really important is the idea of that a statistically significant result only tells us that the observed difference is unlikely to be the result of chance variation. And we've been discussing this all along, but I really want to highlight this because it's going to be important for you to remember that a statistically significant result doesn't tell us for certain that the observed result is not the observed difference is not the result of chance variation. We can never know for certain. This just like when we were getting confidence levels, you can just predict the population parameter with some degree of confidence. We can never know it with 100% certainty. Well, that's the same is true here with respect to, and for the same reasons, more or less. The same thing is true here. When we get a statistically significant result, it's just telling us that the difference is not likely to be due to chance variation. But if you have a 5% probability, if your p-value is 5%, then that's telling you that there is a 5% chance that the difference you observed is the result of chance variation. Okay? So that's the flip side of that. So just to hit that home again, our 5% probability tells us there's a 5% chance or risk. There's a 5% chance that even though you found a significant difference, that difference is actually just the result of chance variation, and you happened to sample and get a sample that has extreme values. Okay. One final idea in this section is that when we look at probability levels, there are one and two-tailed tests. So far, we've just been doing one-tailed tests. And a one-tailed test, it puts all your probability in the one tail of the distribution. So 2.2, what the probability is there, it's actually a little bit less than 5%. But we're just looking at all of our p-value. This is a little bit less than 5%, but I'm going to call it approximately 5%. It's all in one area on this side of the distribution here, because we know that for some reason we are expecting there to be, our sample was greater than our observed value is greater than the expected. But and we can go the other way with a one-tailed test and look at the less than side too. But the point of a one-tailed test is that you have a reason to expect that the test results, that your observed values are higher or lower. But sometimes we go into doing research, and oftentimes we go into doing tests just looking for a difference. We don't know ahead of time if we have an expectation that one group is going to be higher or lower. And when you don't have a good reason for an expectation of the group being higher or lower, or you need stronger evidence for the alternative hypothesis in order to identify it as true, then you should use a two-tailed test. And a two-tailed test takes your probability value and it splits it into two areas. Now what we see here, they haven't quite done it. What they're showing us is that if you have the two tails and you put them at the same area, what we've still got 5% here, but this would be 5% over here too. So there's a total possible risk, a 10% risk of finding a result is significant, but an error. So to help you think about this, let's think about just the p level of 5%. So when we do a one-tailed test, our 5% is all on one side. We'll just think about a z distribution here, and the z value is 2, and the area to the right of 2 is 5%. Now, if we want to do a two-tailed test, but keep a p-value of 5%, then we need to split this 5% in half. And then when we do that, we will see that we can put half on one side and half on the other side. So a two-tailed test with a 5% significance level, if you wanted, you have to split your 5% into two parts. So then your p-value, your z value here is the one where you've got 2.5% remaining beyond Z rather than 5%. And the take-home message here is that with a two-tailed test, you need stronger evidence in order to reject the null, because these values are bigger. They're more extreme values. So a one-tailed test is generally not recommended unless you have a specific reason to expect one group to be higher or lower. Now, it's really easy to do a one or two-tailed test if you're using a statistical program, because it usually gives you the results for both ways. And so you just use the two-tailed test result, unless you came into your experiment expecting a one-tailed result. And again, the point is that a two-tailed result requires stronger evidence in order to reject the null hypothesis. So using a two-tailed test helps us to account for some of the problems we discussed earlier. Another important question here is to take note of whether the result was important or not, because statistical significance isn't the same thing as practical significance. Just because you found a difference that was statistically significant, it doesn't mean that there's some actual practical importance or application of the results. Okay, it just tells us that this difference is hard to explain away as chance variation. Okay, it told you there's a difference that's unlikely to be due to chance. And it's really important to keep in mind that the p-value of a test depends on the sample size. So with a large sample, even a small difference can be statistically significant, and that does not necessarily make it important. Conversely, an important difference might not be statistically significant if the sample is too small. And we've talked about this problem a little bit in the earlier chapters in this unit too. But here or in the lectures on those chapters. So we've talked about this a little bit already, but the thing this is especially important to keep in mind when you've got, there are some very large data sets like we've looked at in the GSS data set. It's a massive data set with a huge sample size. So it's easy to find statistically significant differences. Even a small difference can be seen. You can find a statistically significant difference. So it's important to look at whether or not that difference is likely to be important and the degree of the difference. So for example, with a large sample, it might be more appropriate to only consider p-values less than 1% as significant, depending on what you're looking at. Remember, these are arbitrary values that have been set up, so there's experimenter discretion about what p-value is in your experiment appropriate for determining a difference or relationship dependence. But remember how the p-value depends on the sample size. And this specifically, how these sample sizes relate to your likelihood of finding statistically significant results. But that's not the only important piece here. The model plays an important role too. We need to determine if the difference is likely to be due to chance. And in order to do that, chance must be defined in terms of the study. And the best way to do that is to use a box model in order to help you make sense of what you're testing in your test of significance. Make sure to watch out if your test of significance is based on data for the whole population. Well, because, for example, a test that has whole population data, like census data, it has a heavily inflated, it's the results of, say, a z-test aren't valid because the census, for example, all of the people in the population, so you can get information that's relevant for, say, correlation and regression, but it's harder. You can't really get good tests of significance because there are no inferences to make. The data about the population is there. You're not making an inference from a sample about the population. You know the population, so you can just find out things, what's known about the population in that context. And you also need to watch out if a test of significance is based on a sample of convenience, because a convenience sample is not a random sample. And as you've probably noticed, all of our tests of significance depend on a simple random sampling process. So if you don't have random sampling, then, or especially a convenience sample, then it's very hard to meaningfully use tests of significance. It's also important to consider whether or not the difference proves the point. So a test of significance can only tell you if the observed result is likely to be due to chance variation or not. It does not, the test of significance, it cannot check the design of the study. So it can't tell you if your study is good or not. It can only tell you that a difference is there. It can't tell you the cause of the difference. This is an important point to remember. In conclusion, remember that chance variation is defined by a box model, and how you specify the model is important in determining the test that you choose and how you test the model. The test can only tell you whether a result is likely to be due to chance variability or not. It doesn't tell you for sure if the result is due to chance variability. It will tell you it can't tell you whether the model is relevant or even plausible. It can't measure the size of a difference or the importance of a difference or the cause of the difference. All of these factors, these questions are all up to the researcher to do correctly, to do intelligently, to interpret appropriately. The test can't do it for you. Mathematics can only evaluate the numbers. It can't tell you the meaning underneath them. That's one of the major themes of our whole class here, is that the mathematics, the mathematics part of statistics is an important tool, but it's not the only tool. And the mathematics, in the absence of good, solid logic and reasoning, the mathematics are meaningless. So that intelligent reasoning and reasoning that keeps in mind good study design, modeling of your chance model, that's an essential part of effective use of statistics. Remember that a test of significance can turn out to answer the wrong question, because this gets back to the idea of designing your study well. If you you have to design your study to answer the question that you're asked, that you want to ask. The wrong study design is not going to answer the right question, and the test, and thus the test of significance can't answer the question unless you've set up the study appropriately to get at the question. How do you set up the study appropriately? Well, of course, that's down to, for one, a simple random sampling approach, good study design with respect to choosing the variables, and to how you measure the variables. Finally, tests of significance are incredibly popular nowadays. You'll be hard-pressed to read a journal article that reporting any kind of research article that doesn't have a test of significance. I mean, they're so popular. And one reason is that they're part of an impressive and well-developed mathematical theory. But another reason is that lots of investigators just can't be bothered to set up their chance models, or maybe they don't understand so if you don't set up the chance model appropriately, then you can't test your design either. The language of testing makes it easy to bypass the model and just talk about things as significant or not, and it sounds impressive to to say something is statistically significant. So oftentimes investigators just use apply the tests inappropriately. And so when you're out there in the field applying this material, remember to don't necessarily jump to a test of significance. Remember to evaluate your sampling, evaluate what the question is that you want to ask, so that you can actually get at an answer that is meaningful. And if a test of significance is appropriate, of course, don't hesitate to do one. But it's only meaningful in the context of the model and remembering what your question is. And so throughout our course, we've discussed a whole, the whole gamut of issues that you need to address when evaluating a research project or planning one. And from study design to sampling to describing the participants, describing the variables, and finally describing the comparing variables and looking at, as we did in correlation regression, how they vary together or not. And in significance testing, looking at where there are differences from expected values and whether variables are dependent or independent. And this whole process helps us to understand and answer better hypothesis questions. And this is the basis of science. What we've been doing this whole semester, statistics is the language of science. It's what unites all the sciences. They all use statistics, and the social sciences, the health sciences, political science, economic science. We all use statistics as our common language for communicating about research, results, importance. And when you do science well, you brighten that light of science everywhere. And it's so important to, especially nowadays, to present your observations in their appropriate context and accurately and appropriately. And statistics will help you do that. And hopefully the skills that you've learned throughout this class will help you better evaluate material and science that you are taking in your daily life and in your professional lives. So go forth and brighten the light of science everywhere you can.